Okay, so let me solve you another example so you can see how you can use your knowledge about Laplace transform in order to analyze a circuit in Laplace domain. In this circuit, we do have inductors and resistors, and they are connected to the source right after zero. So basically what I'm looking here, just to remind you, is the step response of an RL circuit. However, we are not planning to solve this in time domain and working with differential equations similar to what we did in 211. Here we want to use the Laplace transform and see how much it's going to be easier to solve this circuit in Laplace transform. Okay, in this circuit, we are looking for I1 and I2 of t. So I1 and I2 in time domain are the goal of this problem. Now, in order to solve this problem, first I have to prepare my circuit. So the first step is preparing the circuit, which means I have to think about my sources and I have to take care of any inductor or capacitor in the circuit. Regarding my source, these two components, these two elements together, the source and the switch, can be combined together and they can be described as 336 U of t, because what the switch is doing for me is basically adding the source right after zero. So it means that together they work as a step function with the strength of 336. So I can remove my switch and describe my source in this form. Now, in order to prepare my circuit for Laplace domain, I have to describe this source, which is 336 U of t, in Laplace domain, and it means that I'm going to have 336 divided by s. So this is what I have to use for my source. Now, for inductors and capacitors, I have to describe them with their equivalent circuit. I don't have any capacitors, but I do have two inductors. How can I describe them? What I have to do is that I have to describe them with their equivalent circuit, which has two components. But before describing them with their equivalent circuit, I need to know what is the initial values. So what is I1 at 0 and what is I2 at 0? Sometimes you have initial values provided by the problem. Sometimes you don't have. If you don't have your initial values and you can see a switch in your circuit, it means that you have to take care of your initial values on your own. So if you have a switch, it means that you have to look at your circuit before zero and solve the circuit, considering that the circuit is stable, and then you have to find your I1 and I2 or whatever initial condition that you need. So if you have a capacitor, you have to find their voltage. If you have an inductor, you have to find their current. But here in this circuit, if I'm focusing on this circuit before zero, this is what I have. And it means if I look at it, I don't have any source in this circuit before zero. Because there is no source, before zero in this circuit, it means that my initial values, all of them, all parameters of the circuit are zero because there is no source of energy. So I1 at 0 is equal to I2 at 0, and that's equal to 0. That makes everything easier because now that I have to describe my inductor in Laplace domain, the equivalent circuit is just Ls. And I don't need to describe my circuit with two parameters. So I'm going to draw the circuit in Laplace domain. So what I have is a source. With a value of 336 over S, and then I have two inductors in series, not in series because there's a resistor here. Okay. And the values of inductors are 8.4, and then I have to multiply it by S. And here I have 10, so I have to say 10S. And this one is 48, and the resistor here is 42. Okay, so this is my Laplace circuit. Now that I have my circuit prepared in Laplace domain, I can solve for my parameter of interest. One of them is I1 and the other one is I2. Now in the circuit, I1 is here and I2 is here. So the best approach to solve this circuit is going to be mesh analysis, because I1 is the current of first mesh and I2 is the current of my second mesh. So I'm going to choose mesh analysis for my solution. So I'm going to start with mesh number 1. In mesh 1, if I start from here, I have a voltage increase, and the voltage increase is equal to 336 over S. Because that's an increase, I have to use a negative here. Then I have a voltage drop across inductor, so I have to multiply its impedance, which is 8.4S multiplied by I1. And then I have the last impedance in mesh 1, which is 42. And its current is equal to I1 minus I2. And then I'm back to the original point that I have started, so I have to say that's equal to 0. Now for mesh 2, if I start from here this time, I have 42 ohm resistor multiplied by its current, which is going to be I2 minus I1 this time. Because I'm writing the KVL for mesh 2, I have to start with I2. The next impedance is 10 multiplied by S. So it's going to be 10S multiplied by I2. And the last one is the 48 ohm resistor multiplied by I2. And again, I'm back to the original point, so equal to 0. Now what I can do is that I can put them in matrices and try to solve for I1 and I2 in Laplace domain. It's pretty straightforward what they have to do here. So the coefficient of I1 in the first equation are 8.4S and 42 here. So I have 42 plus 8.4S. The coefficient of I2 is minus 42. So minus 42. The coefficient, now I have to go to the next equation. In next equation, the coefficient of I1 is minus 42 again. So minus 42. And the coefficient of I2 is 42, 48, which is going to be 90, and 10S. So I have 90 plus 10S. Now let's complete the matrices by filling the constant matrix. The constant in first equation is equal to this term. When it goes to the other side, I'm not going to have the negative anymore. So it's 336 over S. And the constant in the second equation is 0 because there is no constant in the second equation. So I have 0 here. Now, if I call this one as A and this one as B, then it means that I1 and I2 can be described by multiplying A inverse by B. So if you do this multiplication, what you're going to have is over 40 multiplied by S plus 9 over S multiplied by S plus 2 multiplied by S plus 12. And for I2, it's going to be 168 over S multiplied by S plus 2 multiplied by S plus 12. So now I have my solution in Laplace domain. The next step, step 3, is P of E. So for both of them, I have to find P of E. I know that I1 is equal to 40 multiplied by S plus 9 divided by S multiplied by S plus 2 multiplied by S plus 12. It means that I need 3 partial fractions, S here, S plus 2 here, and S plus 12 here. And I need to find A, B, and C. So if you find your A, it's going to be I1 multiplied by S at S equal to 0. And it's going to be 15. Your answer is going to be 15. And for B, you have to multiply your I1 by S plus 2 and then evaluate what you have at minus 2. And this time it's going to be minus 14. And for the last one, which is C, you have to multiply I1 by S plus 12 and then evaluate everything at minus 12. And your answer is going to be minus 1. So now that I have the coefficients, it's very easy to go implement the last step, which is Laplace inverse. So in this step, if I want to describe I1 of t, that's going to be 15. 15 is for this one. B is minus 14 and C is minus 1. So the Laplace inverse of the first term is going to be 15 u of t. This second term is going to be minus 14 e to minus 2t. And the last one is minus 1 multiplied by e to minus 12t. Don't forget u of t at the end. So this is going to be I1. And if you solve for I2, the result of your partial fraction for I2 of S is going to be 7 over S minus 8.4 over S plus 2, and then 1.4 over S plus 12. So you can easily convert this back to time domain. So I2 of t, it will be equal to 7 minus 8.4 e to minus 2t plus 1.4 e to minus 12t multiplied by u of t. Okay, thanks for listening. Have a good day.